What we're going to do now is the E2 elimination of a general secondary substrate. So I'm going to again use the same one I've been using with the other reactions in this set, the SM1 and the SN2. So I've made this one chiral. And what you're going to look for on the arrow to know that it's actually going to go through an elimination instead of a substitution is you need to notice that what's on top of the arrow is a strong base. Now, how do you know if it's going to be a nucleophile or a base? Well, the line is kind of hydroxide. Hydroxide, if you remember from general chemistry, we classified as a strong base. And so if it says hydroxide strength or stronger, by looking at your pKa table, you should know that it is a strong base. So OH minus, or the RO minuses, which are the deprotonated alcohols. You could also use a deprotonated alkyne, a deprotonated alkene, a deprotonated alkane, or a deprotonated amine. All of those would be strong enough bases to do an elimination with a secondary substrate. If you have bulky or non-bulky, it can affect whether you make a more substituted or a less substituted alkene as the major product. If again it is a tertiary substrate that you are doing this with, if it has a negative charge, it prefers to go E2. And all of this information is on that chart that is an I-learn. I'm going to use this secondary substrate, and I'm going to keep it simple so that we are looking at this, but I'm going to use an alkoxide. I'm going to use methoxide. And again, you would have some cation to balance it. Doesn't really matter. And typically the solvent would be the corresponding conjugate acid for these systems. Okay. Now this particular base is a non-bulky strong base. And what you're going to do is you're going to remove a hydrogen from one of the adjacent carbons to the carbon with the leaving group. So bromide is the leaving group in this particular case. And since this is a non-bulky strong base, it tends to favor Zaitsev's rule. So our base here, this oxygen really wants a proton. And so it will remove a hydrogen on one of these adjacent carbons that are underlined in green. It's more likely to do it from the one I've just shown. And as a result of that, the carbon-hydrogen bond breaks. You're able to make a carbon-carbon double bond, and the carbon-bromine bond breaks, and the electrons go to the bromine because carbon likes to have just 4 bonds. Okay. So the product that you would form as the major product in this particular case you have to go back and look at what I had. Okay. Would have a methyl group here, a hydrogen here, methyl group here, and a methyl group here. This would be the major product. The minor product is also possibly formed. And this would be our minor. And then you would also have methanol as the corresponding conjugate acid from this reaction. The major product is a more substituted alkene. As you can see in this case, it's tri-substituted. And the minor product in this particular case is a mono-substituted alkene. And I know which one's major and which one's minor by the type of base I am using. If I am using a strong non-bulky base, I tend to favor the more substituted alkene like I've shown here. If I wanted the minor product to be the major product, I'd be needing to use a strong bulky base, something like tert butoxide, to make this happen.